let's get started. Okay, so today we are jumping into, finally, derivatives. So I told you the big four ideas of calculus are, first, the idea of a limit, a convergent sequence, same thing. Then I said the idea of continuity, what it means for a function to be continuous. Now we're going to be looking today at derivatives, which are a special type of limit. And then the last chapter will be on integrals, which is another special type of limit. So that's where our last two chapters are going to be on derivatives and integrals. And in one respect, they're like inverse functions of each other. So today we'll start with the derivative. If you've ever heard someone talk about a derivative before, chances are they've said something to you of the effect, it's the slope of a function at a point. What's the derivative of a point? What's the derivative of a function at a point? It's its slope at a particular point. So you know what the value of a function is at a point. We think about that as the height of the function, right? So I've got this line here. What's the value of this function at 4? It's 3. Now we're going to come up with another concept called, well, and you also knew the second idea that we talked about, this was at the very end of the last chapter, was the limit of a function as it approaches a point, which if the function is continuous at that point, and it's the value of the function at the point and the limit of the function as it approaches that point are the exact same thing. The only weird case was when the function wasn't quite defined there and you had like a little hole. And if you put a little hole here, so we say pretend that this function wasn't defined at that point for some reason, the limit of the function as it approaches that point is still exactly what you expect it to be, even though the function is not defined there. Right? And the intuition for the limit of a function as it approaches a point is the value when we get really close but not quite there. Ringing some bells, bringing some ideas back. Okay, so we're going to be talking about the derivative. Intuitively, it's the slope of a function at a point. We all have our going clear back to, I don't know when you first come across this, but at the very latest middle school, you're taught that the slope of a function is rise over run, right? That's the exact same intuition that we're going to use to try and come up with what kind of function should we use to get the slope of a function at a point. So let's start with a really simple function, a function that's just a line. Now you know how to get the slope of a line. Here's the way that you did it back in middle school. You had 2 points on the line. Pick any 2 points you want, doesn't matter. Then you look at the run between those 2 points and the rise between those 2 points. Take its ratio, that's the slope, right? So this function, when we go over 6, we go up 2. So the rise is 2, the run is 6. The slope of this function is 2 over 6, or 1/3. Nothing weird, right? Here's our basic equation to do that. Pick 2 points. If we call this point over here x1 and we call this point here x2, then f of x1 is the height of this, and f of x2 is the height of this. And this is our generic equation for calculating the slope. So if we have 2 points, x1 and f of x1, x1 is the x value, f of x1 gives you the y value for a specific x value, right? So x1, f of x1, that's a point. In this particular case, it's -2, 1, but in general, we would just say x1, f of x1. In our particular case, -2s are x, 1s are f of x1. Same thing over here. Here's our x2 and our f of x2. The way that we can calculate the slope is we do the difference in the heights over the difference in the runs, if you want to think about, or the difference in the rise versus the difference to get the runs. I don't know how you want to say that. Either way, plug in to the equation exactly the way that we know. We call this one x2, so f of x2 is 3, and we do minus f of x1 is 1 over x2 is 4 minus x1 is -2, and that's exactly what we get, 2 over 6, or 1/3. Nothing weird, pretty straightforward. Slope. Okay, now you might not remember this exact equation for a line, pretty basic form of an equation for a line. We call it the point slope form, I think, something like that. It gives you the equation of a line if you know the slope and a particular point, x naught, y naught, that the function goes through. And this is one way to get the equation of the line. You might be used to y equals mx plus b. That's a special case of this where the x naught you choose is 0, and f of x naught is what b is. It's the y-intercept. It's where the function is when x is 0. So that's just a special case of this exact formula. Anyways, so if we were to find the equation of this line, how do we do it? Y naught, we can pick either of these points to be x naught and y naught. Pick whichever one we want. I'll use this one just because no negative values, probably nicer. So.
Wait, what? That's
so,
on the x-axis.
Yeah. Oh, I'm picking a point, so I'm going to pick this point to plug in for y naught, x naught. So my x2 and x naught are going to be the same thing, and my y naught and f of x are going to be the same thing. So you just fill it out, gives you the line. So we have y naught y naught, oh, thank you, 3. Y naught plus m, we just figured out m is 1/3, x minus x naught, which is 4. And there's the equation of our line. And you're used to doing this. Nothing weird, right? And you can get that in mx plus b if you want, just simple algebra from there. But that's the basic equation. Okay. Obviously, what would that be? Negative 4/3 plus 3, well, 5/3, so the y-intercept's 5/3, which I did that pretty good. Okay, so that's looking at a line. So now, what's the slope of the line at any point? 1/3, right? The slope of the function at this point is 1/3. The slope of the function at this point is 1/3. The slope of the function at this point is 1/3. Doesn't matter what point you pick, the slope's the same. That's the defining feature of a line. The slope's the same. Right? So we know what the derivative of this function now is at any point. For any point, and the typical symbol, if f is our function, we use f prime for the derivative. We know f prime at any point x is equal to 1/3. Very concrete case. We'll come up with generic ways of deriving these, but I just want you to understand the idea. Here is our slope function. Give me any x you want, this function gives you the corresponding slope. It's just 1/3, doesn't matter what point you pick. The derivative function of this function is a constant. It's just 1/3. The slope everywhere is 1/3. Here's the function that no matter what x you give it, it gives you the slope at that point. Does that make sense? So this is it in a simple case. Now we're going to look at a more generic case and try and come up with a similar thing. So now let's say we have a function. Who knows what it's doing? But the point is, it's not just a nice, well-behaved function that's a nice straight line. And obviously, the slope of the function here, and the slope of the function here, and the slope of the function here are all very different. Is that intuitively making sense? So how do we find the slope? So imagine I gave you some specific function that was curved this way. And I said, at this point, I want you to give me the slope. Find the slope at that point. How would you do it? If I told you to estimate it, how would you do it?
Well, to estimate it, you could just choose where it's relatively straight, and then choose 2 points and do the same.
So yeah, you kind of got the idea. So we know how to get a slope when we have 2 points, right? I can find the slope from this point to this point. So I can find this slope. I know how to do that real easy. So if I use this point and this point, it gives me the slope of that line, and maybe that's pretty close to what we want, right? But notice in general, if I were to pick this point to be closer, say I would have used this point and the point right here, I would have gotten an even better slope. And if I would have used a point even closer, I would have gotten an even closer slope. So here's our point x naught, here's our point f of x naught. That's an x naught, not an x1. I probably wrote it as an x1, but it's supposed to be x naught. So there's some point. If we want to calculate an approximation of the slope of that point, we could use this formula. The slope at that point, I mean, I typically use m for the slope, and m naught means the slope at x naught. So the slope is roughly f of x naught minus f of x over x naught minus x for some other point x. But notice as I choose an x closer and closer and closer to x naught, my slope becomes a better and better and better approximation. So the whole idea of a derivative is we're just going to define the derivative at that point to be this limit. The limit of the slope as our points get closer and closer and closer together. As x approaches x naught, take the limit of the slope that gives us, that's our derivative. That's all it is. This quotient, just for terminology, in case I accidentally say it without explaining it, we call this the difference quotient. It's the difference of two values in a quotient, the difference quotient. So I might accidentally say over and over again, you take the limit of the difference quotient, talk about a derivative. If you were to go ask some random mathematician, hey, what's a derivative? Oh, it's just the limit of a difference quotient as x approaches x naught. They'd probably say something close to that. And that's just the way you think about it. So this is very common terminology to call this a difference quotient. You should know, if I say difference quotient, exactly what I'm talking about. That thing. Rise over run, slope. Anyways, so that's the whole idea of a derivative. So if you could calculate limits, we're just calculating a special type of limit now. There's nothing crazy about it. There's nothing, it's just that. So we'll do some terminology, then we'll do a bunch of examples, and we'll go on our merry way. Now, this was all just high level. We'll give the exact definition down here. Okay, so now we got intuition for everything we're covering. Let's get into the nitty-gritty. An interval, an open interval, AB, where we all remember what that stands for. That's not a point. That's all the set of points whose value is greater than A and less than B. Right? So an open interval AB containing x naught, so x naught is some point in AB, is called a neighborhood of x naught. What's a neighborhood of x naught? It's an open interval that contains x naught. That's what a neighborhood is. Common topology terminology. Yep. Anyways, so from here on out, anytime I use I, it's going to be typically understood I is a neighborhood containing a point called x naught. And I'm not going to want to explicitly say that every time. Anyways, let I be a neighborhood of x naught. Then the function from I to R is said to be differentiable at some point x naught, provided that this limit exists. In which case, we call it the derivative of f at x naught.
In what case would the limit not exist?
We'll see cases where it doesn't exist, but intuitively it's where the slope can't be defined. So if my function looks like this, it's not going to have a derivative right there. So that's intuition for it. And if it's not continuous at the point, it can't have a derivative there. So if I've got a function that goes like this, doesn't include this point, but then starts here and continues, it doesn't have a derivative at this point. So if it's not continuous, or the slope doesn't exist, or it's not defined at the point, obviously, then there's no derivative.
What does it mean for that slope to not exist? Because it seems like at that point it might just be 0 or something. It might be 0. Well, because, I mean, when we talk about the slope of a line, what we're really talking about, that's our intuition for it. What we mean is the slope of the tangent line to that point. And this is a tangent line, this is a tangent line, this is a tangent line. Lines that just barely intersect that one point. And so there isn't any one slope. Okay.
A more intuitive one that we'll do will prove that the absolute value function doesn't have a slope. And it looks like that. So the slope is a constant, 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 constant. Then what do you call it there? Suddenly 0, and then some other constant. Because I think one of the things we'll prove later on is, well, that's too much of a leap. That won't be useful to you. Anyways, so that's what we mean by the derivative.
Here's its exact definition. Typically, I wrote up here. Typically, this is the notation we use for a derivative. So if I do f prime at x naught, this is interpreted as the derivative at x naught of a function f. Right? So this is shorthand for this thing right here. The limit as x approaches x naught of the difference quotient. The limit of the slope is another way you can think about that. As we get closer and closer to the point x naught. Good? Alright. So, still not examples. Let's see. Definition. If f is a function from some interval to r is differentiable at every point in I, then we call f differentiable. It's the exact same definition we had for continuous. Remember we talked about a function being continuous at a point, and then if it's continuous along its whole domain, we call the whole function continuous. So it can be continuous at a point, or the whole function can be continuous. Same thing. What can I do for you?
Are you missing any students?
Nope. Same thing, we can have it differentiable at a point, and if it's differentiable at every point, then we call the whole function differentiable. So if I tell you this is a differentiable function, that means it has a derivative at every point. The derivative always exists.
So the absolute value function is differentiable, but it is differentiable everywhere except for...
Yeah, if you restrict the domains like you don't include 0, it's now a differentiable function. But with 0 in there, it's not a differentiable function. Okay. That's that. Let's come to this. If f is a function from some interval to r, some neighborhood of x naught, that's implied when I use a psi. So if f is a function from some neighborhood of x naught to r, and it's differentiable at x naught, we call the line, notice the parallels with this exact equation, f of x equal to f of x naught plus the derivative at x naught times x minus x naught, the tangent line to f at the point x naught f of x naught.
So how is it...
Do we need to see a picture of that, or?
I think I understand that. How is a tangent line defined in trig without using this definition?
Just a high level, well, I've never been through a good rigorous trig book, so I don't know. It's a short
Seems
answer.
like that is a very calculus definition.
But when you talk about the tangent function in trig, it's defined in terms of sine and cosine. Right? Tangent function is just sine of theta over cosine of theta. And that's its definition. So usually you start by defining sine and cosine, and then all the other trig functions just fall out of that for free. But, yeah, I don't know how you define it in, I can't remember the definition in geometry. I have a good geometry book, so it's most likely got a good definition in there. But yeah, I don't remember exactly what the definition is. But yeah, so let's draw a picture just in case to maybe you think you understand, but maybe there's some subtle point that's being missed. So here's a random function. Here's some access. So we're saying pick some point x naught, then f of x naught is right here. And so we've got this point. This point, if we write out the coordinates of this point, is just x naught comma f of x naught. And we're saying the tangent line, we're saying the line that only goes through that point and doesn't intersect the function anywhere else. Well, anywhere else nearby. It can intersect a core down here, but not any points directly by it. Although I know that doesn't really make sense to you because you're not in topology. But in topology, we would say the line that doesn't intersect every neighborhood around that point except for at that point. But that doesn't matter. Anyways, here's the line that we're talking about, the tangent line. It just goes through that point, but no points next to it. So all the points, if you look at the points really, really close to it, doesn't go through any of them, just at one point. If you got way, way zoomed up, then we're going to exaggerate the curve there. And there's just that one point that it barely goes through. That's the tangent line intuitively. So we're saying the equation of this line now is this line that I just drew. The equation of that line is f of x is equal to f of x naught, whatever that value is, plus f prime of x naught, the slope, times x minus x naught. And that's a times. I should use dots when we have function notation next to parentheses.
Is there only one tangent line for every point?
Yes.
Is there one for every?
There has to be a derivative defined there.
Okay.
So if we have a point such that it's differentiable at that point, so that this is defined, then now this whole thing is defined. So this whole thing just depends on this being defined. So if this is defined, then this whole thing now makes sense. Because these are just constants, and these are just variables.
Do we do a proof of that? That there's only one?
You get it for free if there's only one of this.
Right.
Because once you have a value for this is a unique line.
Right.
Okay, so that takes care of the tangent line, and I'm almost positive, but I don't remember for sure, that a bunch of your homework problems are like, here's a function, find the tangent line at this point. And so that's how you do it. Okay, now we get to examples. Okay, so our first proof, I didn't write them out perfect over here, I just gave me enough that I knew exactly what I was doing. So, if f is a function from some interval to r, well, this one, yeah, we can just write out. Let f be some function from some open interval to r by f of x is equal to mx plus b, not let, if. If this is the case, then the derivative at every point is just going to equal n. That's what we're going to prove. We're going to prove that the derivative of a line is just some constant, the slope of the function. The slope of the line. That's what we're going to prove. Good? Alright. 1. Let's see. Well, we'll start with our let, I guess. Let f from I to r by f of x equal to mx plus b. 2. Then, there's two ways we could do this. I don't know if you want me to use the x's in general, or if you want me to grab an arbitrary x naught in I and do it. Maybe I'll grab an arbitrary x naught in I so that we can see the same notation. So let x naught be any point in the domain, and I'm going to show that the derivative at that point is equal to n. Therefore, the derivative at every point in the domain is equal to n. You follow my thinking? So let x naught be some point in I, comma, then f prime of x naught. By definition, what is that? That is the limit as x approaches x naught of f of, which one did I do first? X naught first? F of x naught minus f of x all over x naught minus x. Point of interest, the order that you write these in doesn't matter as long as you do it in the same top and bottom. Because if I times this by a negative, that flips. This by a negative, that flips. I time top and bottom by a negative is equivalent to times n by 1. So, doesn't matter which way, but I'll try and be consistent. So, f prime is equal to this, but what's that equal to? That's equal to the limit as x approaches x naught of, what is f of x naught?
M times x of...
Yeah, look at the definition of our function. Don't lose track of what our function is. We know what our function is. It's mx plus b. That's what f of x is. So f of x naught is m times x naught plus b. M's just a constant, b is just a constant. Right?
Okay.
Like over here it was, what was that? I can't remember. 5/3 I think, and the slope was 1/3. So m's just a number like 5/3, b's, or m's just a number like 1/3, b's just a number like 5/3. They're just constants. And we're showing that it doesn't matter what those constants are, the derivative is always whatever this constant is, m. Follow me? Okay, so then f of x naught is m times x naught plus b. And then we're going to minus f of x, which is mx, and then we have a minus b. You follow all the algebra there in the numerator, distributing the negative. I'm minusing f of x, so I'm minusing this and I'm minusing this. Weird? Let's write it this way. Maybe I'm doing too much in one step. Minus f of x is mx plus b. And we'll put parentheses there to show that that was f of x naught, all over x naught minus x. So we have f of x naught, the value of the function when you plug in x naught, minus f of x, the value of the function when you plug in x, all over x naught minus x. Now this is equal to, and now I'll do the algebra, mx naught plus b minus mx minus b all over x naught minus x. Oops. It's equal to the limit of this. Don't lose track of the fact that we're taking a limit as x approaches x naught. Okay? And this is equal to the limit as x approaches x naught of b cancels out with b. So I have mx naught minus mx in the numerator. N's just a constant. I can factor constants out of limits. So this is the same thing as, well, we'll do that in the next step since I already wrote my limit. So this is m times x naught minus m times x all over x naught minus x. Okay, now that's equal to, pull m clear out the limit. So m times, maybe use parentheses to make sure I see that m's outside the limit now. The limit as x approaches x naught of x naught minus x over x naught minus x. What is x naught minus x over x naught minus x? But wait a second. Am I not doing 0 divided by 0?
It's 1 as long as x isn't equal to x naught.
How do I know that x is never equal to x naught?
Because it's a limit, you never reach it.
So the way that we define this limit, we defined it is x is approaching the value x naught but is never equal to x naught. That's what we specifically define. I don't know if you remember when we talked about a limit point. I think you guys were both gone for that lecture, but hopefully you went back and watched it. And maybe go back and watch it if it doesn't make sense to you that x is never actually equal to x naught. And we specifically defined it that way. Because we defined this limit using our other notion of a limit. You remember that?
Yeah, but not as good as the rest of it. I remember going through it. I mean, I went and looked at the book and watched the lecture.
The limit as x approaches x naught of x is the same thing as the limit as n goes to infinity of x sub n, where x sub n converges to x naught, but we restrict its domain so that it never actually uses x naught. So it's a way of reworking this limit. Anyways, so yeah, we've got the limit as x approaches x naught of 1 times m. What's the limit of a constant?
It's a constant.
Just a constant. The limit of 1 is just 1. As x approaches x naught, 1 stays 1. A constant stays a constant, it doesn't change. So this is n. Anything weird? Anything explained, or just better to move on to another example? Because we're done. We just barely proved that the derivative of a line is just its slope.
So, how does that work with your tangent line? Because they would intersect the line at every single point. Wouldn't it?
How would this work with my tangent line?
Yeah, so if you have your tangent
My
line,
tangent line to what? To this function?
Yeah.
Oh, the tangent line is the function.
Yeah.
Yes.
That's my saying, it intersects it everywhere, not at one point.
Yeah. The tangent line of any point on a straight line is the line.
But doesn't that, is that, Right, the definition doesn't imply that it intersects at one point, but it does usually intersect at one point, right? It's not-
Yeah, it intersects at one point or, well, no. It intersects at one point locally, is one way to say it. If you look on a really, really small scale, it intersects at one point. Or they coincide. I'm sure that there's that exception.
Right.
Okay. So, that's the proof that the derivative of a line is just a slope. Now let's move on to some other one. Next, we're going to prove if f is a function from R to R by f of x equal to x squared, then f prime of x is equal to 2x. So we're going to prove that the derivative of this function is this function. And let's draw a picture of this one so that you understand exactly what I'm saying. We'll pick a particular x squared. We won't use, well, yeah, we'll just use that exact one for now. You all understand what the function x squared looks like? Parabola. We'll draw it out real quick. And draw it down here so that you don't have to erase the part proof. So we've got some coordinate system. 1, 2, 3, 4. 3 should be plenty. Something like that. Okay, so just trying to parabola. When you plug 0 in for that, you get 0. When you plug 1 in, you get 1. When you plug -1 in, you get 1. When you plug 2 in, you get 4. When you plug -2 in, you get 4. When you plug 3 in, you get 9. And when you plug -3 in, you get 9. And it shoots up on both sides. And not a chance I'm going to be able to make this look good. But I think you get the point. Something like that. Parabola.
Is it negative though?
Positive. Any number squared is positive.
Right, so why is that on the negative side?
That's when you plug in a negative x. So when I plug in -2 to that function,
Oh, right.
I get 4 out. Okay, so now we're saying the derivative of this function. Pick any point you want. So for example, over here at 3, what's the slope of the function at 3? I'm going to prove that it's 6.
Okay.
What's the slope of the function over here at -1? I'm going to prove that it's -2. So the slope of that line going through that point, its tangent, will be -2. It's going to be 2 times whatever the x value is. That's what gives you the slope. It's that easy. Make sense what we're proving? You understand what I mean by the slope is 6 at this point. I mean, if you were to draw the tangent line through that point, can't do it, but I'll try, then this line would have a slope of 6. If you found 2 points on it and calculate the rise over run, you'd get 6. Every time you go over 1, you go up 6. And then the slope over here is -1, or -2. What I mean is if you go over 1, you go down 2. That would be the slope of this tangent line. So that's what we're proving. So let's prove it.
In this case, the tangent line for 0 is 0.
Yes. That is correct. So let f be some function from R to R by f of x is equal to x squared. Let x naught be any real number. So it remains to show that the derivative at x naught is 2x naught, and we're done. Make sense? Because x naught is any real number, we're proving that the derivative for any real number x is just 2x. That's all we're trying to prove. So, let's do it. Then, f prime of x naught is equal to, it's f of x naught minus f of x over equal to the limit as x approaches x naught of f of x naught minus f of x over x naught minus x. This is equal to the limit. I'm not going to bother writing that anymore. You know that's the limit we're always doing. F of x naught, when we plug that into the function, we get x naught squared minus, when we plug x into the function, we get x squared all over x naught minus x. Nothing weird there, right? Which is equal to the limit of, that's a difference of squares, so we factor it, x naught minus x, x naught plus x, all over x naught minus x. Now the product of the limits, or sorry, the limit of a product is the product of the limits. So this is equal to, I can split that into 2, that's the limit of, maybe I'll use parentheses, x naught plus x times the limit of x naught minus x over x naught minus x. So I'm just factoring that into its own separate limit. So the limit of the product of two terms is the same thing as the product of the limit of those two terms.
Why not just cancel them? Inside the limit.
Or you can do that. Perfectly fine. I just wanted you to see that we're using the exact same step that we did last time, because a lot of limits reduce to try and get this isolated by itself and then let factor out. Because maybe you don't remember this, and I should have specified it from last week. A lot of the times the way that we find the limit is we just take the limit, we just plug in the value. The reason that we can't ever do that with the derivative is because of this denominator. If I were to just plug in x naught for x, I get 0 in the denominator. So the whole trick when you're working with derivatives is to try to get this out of the denominator so that you can just take the limit. That's the whole trick. So notice I know how to take the limit of this thing now. We're never going to divide by 0. This I don't know how until I realize, oh yep, that's just 1, and then we're good. So this is the limit, and maybe I'll put the x naughts back in. As x approaches x naught of x naught plus x times 1. Now I know how to take this limit. I can just plug in x for x naught. Or x naught for x. Sorry, I said that backwards.
Isn't x naught just a constant?
Yeah, so I'm doing it as x approaches some constant number x naught.
I was just thinking, wouldn't you do, you'd split it up into the sum of the limits, the limit
Oh,
of
yep,
x naught.
you could do that if you wanted. So we could call this the limit as x approaches x naught of x naught plus the limit as x approaches x naught of x.
Which is x naught.
The limit of a constant is just a constant x naught. The limit as x, the limit of x as x approaches x naught is obviously x naught. So that's equal to 2x naught, and we're done. Follow that? Anything weird? Okay.
I can tell if that was a period or if x not up there.
Oh, sorry. This one's a period. Okay. Let's
Will we be doing a lot of proofs like that, where it's, here's a function, find the equation of all the derivatives?
I don't know, because we're going to come up with generic formulas that you can always use. These are just very specific examples to help get you a feel for how you calculate these limits. I'm not sure what I gave you in the homework. I might tell you calculate this derivative by hand, meaning don't use the formulas. But we'll give you formulas for calculating these things. I mean, I could go pull some random calculus student off the street and ask him to calculate the derivative of this thing, and they could do it in 2 seconds. If I asked them to prove it, they wouldn't have a clue where to start. So, and Emma's laughing because she knows how true that is. That's a very easy derivative to calculate, and we'll teach you how to calculate those derivatives. It's a very easy operation. But what you're doing behind the scenes and how to prove what the derivative of something like that is a whole other story. So, you'll be able to calculate these things. That won't be your problem. Your problem will be, can you prove what it is? And we'll give you the generic formulas for calculating them. Anyways, so that was that one. Let's move on. Let's prove that if f is a function from R to R by f of x is equal to the absolute value of x, then f prime at 0 doesn't exist. You can't take the derivative as 0. That's what we're going to prove. We're going to prove that the limit as x naught approaches 0 doesn't exist. Now, one of the ways that you can prove that a limit doesn't exist is you can show it's converging to two different values. If it's approaching two different values, then it can't be well defined, right? It can't have two values and be well defined. So we're going to show that this isn't defined, it doesn't exist, because we're going to show that you can get two different values with this. And obviously it's going to be -1 and 1. Make sense? Okay. So 1, let f from R to R by f of x is equal to the absolute value of x. Then the limit as x approaches 0, so I'm showing that this isn't defined. So the limit as x approaches 0, where x is greater than 0. So I'm saying, let's draw this function real quick. Maybe draw it down here so it's not right. So the function just looks like a v, the absolute value function, right? So I'm saying, look, we're going to pick a sequence of terms in the right-hand side that converges to 0. Then I'm going to take the limit when we use that sequence. And then we can take a sequence of terms that approaches 0 from the left-hand side. And it's always going to be negative. We've done very similar stuff to this for like showing that a function isn't continuous at a point. Right? We had a function, it was always 1 as it got to 0, and then at 0 it jumped down to -1. We took two different sequences, one always positive, one always negative, converging to that point to show it wasn't continuous at that point. You remember doing problems like that? It's the exact same idea. We're taking a sequence in the right-hand side that's always positive, so I'm taking a sequence of terms that converge to 0 that are always positive. They're over here. And that's going to give me a derivative of 1. And then I'm going to take a sequence of terms that converge to 0 that are always negative, so a sequence on this side that gets closer and closer to 0. And my derivative is going to be -1. Since I got two different values for my derivative, it's not defined. It doesn't exist. Make sense? Okay. So then the limit as, and maybe it would also help to kind of draw a picture of what this derivative function looks like. So when we take the derivative of that, maybe this will help with intuition. So here is 1, and here is -1. So the derivative function of that, the derivative at all these left-hand points is always going to be -1. So it's -1, -1, -1, -1, -1, not defined as 0. And then at 1, or for any positive value, it's always 1. So then up here it's 1, 1, 1, 1, 1, 1, 1, 1, 1. So there's the derivative function of this function. So if this is f of x, then here's f prime of x. Does that make sense? And so obviously this function isn't going to be defined at the point 0. Or it doesn't have a limit as it approaches 0, isn't in the exact same way of thinking about it. Here's our f prime function. It's not going to have a limit as you approach 0, because if you approach up here, you're going to get 1. If you approach down here, you're going to get -1. So it doesn't have a limit at that point. And I don't know, this might have been a homework problem, come to think of it. Where they gave you the function, it's always 1 if it's positive, -1 if it's negative, or equal to 1 and 0 included somewhere. They probably filled in the dot on one of these. Yeah. Anyways, let's just do it. So then the limit as x approaches x naught, where x is always a positive number, of, we have absolute value of x, sorry, you okay with me skipping straight to plugging in? F of x naught minus f of x, because this is what f of x is. f of x naught minus f of x over x naught minus x. Okay with that? Just plugging in directly. Okay, so this is equal then to the limit as x approaches x naught, or as x approaches 0, and we know that we're doing it where they're always positive, of x naught is 0. Sorry, why am I plugging in x naught? 0. We already know what x naught is, it's just 0. Making a mess. So, that's my x naught, right? And f of x naught. My x naught is 0. X naught, x naught. Okay, absolute value of 0 is obviously just 0. 0 is just 0. Let's look in the numerator. What's the absolute value of x if I know x is positive? It's just x. So in our numerator we just have negative x. In our denominator we just have negative x, which is equal to the limit as x approaches 0 from the positives of 1, which is equal to 1. Okay? Also, the limit as x approaches 0, where x is less than 0, of absolute value of 0 minus absolute value of x over 0 minus x is equal to the limit as x approaches 0, where x is less than 0, of, what's the absolute value of x if x is negative?
Negative x.
Negative x. So we have negative x in the numerator, negative x in the numerator over negative x in the denominator, which is then equal to negative x's cancel out and we get negative 1. Any questions there? Okay. Therefore, the limit doesn't exist. Because we got two different values for it. F prime is 0, doesn't exist. Sorry, I should have started these with f prime of 0. F prime of 0 is this, f prime of 0 is this. So I got f prime of 0 equals 1, and f prime of 0 equals negative 1. No, yeah, okay. So that's absolute value. Okay, so now let's prove our first generic formula for calculating a derivative. So if f is a function from r to r by f of x is equal x to the n, where n is a natural, or n in n. Oops.
Would it not n in z?
No, we're just going to prove it for. Is 0 a natural number in this class? No. So yeah, we should be good. I was going to say we might need to do positive integers. So we're just taking positive integers right now. So if f is a function from r to r by f of x is equal to x to the n for n in n, then f prime of x is equal to n times x to the n minus 1. So quick example, if I know that f of x is equal to x to the 19, I'm saying f prime of x is then equal to 19x to the 18. If it's x to the n, the derivative is n times x to the n minus 1. That's what we're proving. You see it now? Alright, so let's calculate it. 1, let f be some function from r to r by f of x is equal to x to the n, comma, and let x not be any point in r. So it remains to show that f prime of x naught is equal to n times, where n's a natural number. Sorry, I should have put that in there. Understood, n's a natural number there. Okay, you with me still? Didn't lose you? Not with me?
No, you didn't lose me.
I didn't, oh, yeah, I shouldn't ask two questions where
Yeah.
both answers can be negative. Okay. Okay, now we're finding the derivative. So then the limit as x approaches x naught of f of x naught minus f of x over x naught minus x is equal to, I'm not going to bother with the arrows under the limit anymore, I'm just going to write the limit of, what is f of x naught? That is x naught to the n minus x to the n all over x naught minus x. Still with me? This is equal to, I'm going to factor out an x naught minus x from here, cancel them out here, and that's going to leave me with the remaining terms. So this is equal to the limit as, factoring from the top, an x naught minus x leaves me an x naught to the n minus 1 times x to the 0 plus x naught to the n minus 2 times x to the 1 plus dot 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 plus x naught to the 0 x to the n minus 1. That's way back to preliminary stuff. So it's that all over x naught minus x. Now I can cancel, I'll just cancel out my x naught minus x's, and that just leaves me with the limit of this expression. So this is equal to the limit of, maybe we'll do parentheses so I lose track. So we have x naught to the n minus 1 times x to the 0. Well, x to the 0 is 1, so we don't need to write the x to the 0. Plus x naught to the n minus 2 times x to the 1, plus, maybe I'll write a couple more terms to make sure we see the pattern. X naught to the n minus 2, oops, this was minus 2, this was minus 3, minus 3 times x squared, plus dot dot dot, we'll write the second to last term, will be x naught to the 1 times x to the n minus 2, and then our last term is going to be x to the n minus 1. Follow all that? The pattern is, as we decrement the left hand's exponent, we increment the right hand term's exponent. So it's 0, then 1, then 2, then n minus 1, then n minus 2 all the way up to n minus 1. Concrete example, maybe that will help. If I have x cubed minus x naught cubed, any difference of terms to the same power, this can be rewritten as x minus x naught, factor that out, times, and I'm going to write this a little bit weird to help you see it, it's going to be x to the 3 minus 1 times x naught to the 0 plus x to the 3 minus 2 times x naught to the 1 plus all the way down to x to the 1 times x naught to the 3 minus 2. Using the 3 the same way we're using n up here. So obviously that just reduces to x minus x naught times x squared plus x times x naught plus x naught squared. No doubt you've done that several times. So same formula. Just doing it for n number of terms, we have no clue how many. Could be 3, could be 100. We still good? Okay, now we know how to calculate the limit of this thing. We no longer have that pesky denominator. We don't have to worry about dividing by 0, taking our limit. We're now ready to do the limit. This is as x approaches x naught. We can just now plug in x naught for all our x's.
So,
The only reason that we couldn't do that up here is because otherwise we'd be dividing by 0. The whole trick is get to the point where I can just plug in x naught for x and I won't be dividing by 0. Once I reduce it to a point where plugging in x naught for x doesn't cause me to divide by 0, we're good. If you go watch the very last lecture that we did before the break, it's one of the points I tried to stress is don't kill yourself taking these limits. Most of the time, you just plug in the value. It's only when plugging in the value somehow breaks the function that you then need to start being clever and tricky. Okay? So we got to the point where, yeah, we know how to take that limit. That's real easy. Just plug in x naught. So now this is equal to x naught to the n minus 1 plus, I have x naught to the n minus 2 times x naught. So I have n minus 2 x naughts here and x naught here. How many do I have total?
N minus 1.
N minus 1. X naught to the n minus 1. You follow that? Because I'm plugging in x naught for x. And when you multiply terms together, you add the exponents. N minus 2 plus 1, just n minus 1. Let's do it for the next term. Plus, so we have n minus 3 x naughts here, and I'm going to have 2 more x naughts here for a total of how many?
N minus 1.
N minus 1. So x naught to the n minus 1 plus dot dot dot, and obviously x naught to the n minus 1. Okay, how many x naughts do I have? How many of these terms do I have is what I need to say.
N.
Are you just looking at the answer, or did you think about it?
Alright.
Okay, yes, there's n of them, right? Because we go from n minus 1 to 0. If you look at all the numbers from 0 to n minus 1, that's n numbers. So yeah, so we have n x to the n minus 1s. That's exactly right.
Goes from n minus 1 to 0.
Yeah, if you look up here, we have x naught starts at n minus 1, and then it's n minus 2, n minus 3, all the way down to 0.
Okay.
Plus x naught to the 0 times that. So it's 0, then 1, then 2, then 3, then 4, then 5, all the way up to n minus 1. How many numbers do we count? N numbers. Follow that? Probably would have been easier to see it if I would have written this as a sum. The sum from 0 to n minus 1 counts n terms.
Is it just using, are you using the binomial theorem there?
In factoring this out,
Yeah.
no.
No, because that has the
The binomial theorem, yeah, is about the coefficients. But yeah, I could have rewritten this as this, we're taking the limit as x approaches x naught, the sum from I equals 0 to n minus 1 of x naught to the n minus 1 minus I times x to the I. So when you plug in 0, we get x naught to the n minus 1 times x to the 0, that's our first term. When you plug in 1 for I, n minus 1 minus 1 is n minus 2 for our x naught term. Plug in 1, that gives us this term, etc. And then when you look at it this way, this obviously, all the numbers from 0 to n minus 1 is n terms. So maybe that would have been a better way to do it, I don't know. Same idea. But anyways, yeah, so it's equal to that, and that's what we were after, so there it is. Any questions? So now, there's a bunch of derivatives that you instantly know how to calculate. You know that the derivative of x to the 13, if I want the derivative of that function. So the derivative, sometimes we just put parentheses around it and put prime like that, say its derivative is just equal to 13x to the 12. And you can do that no problem. You don't even have to think about it.
Depending on what x is.
Doesn't matter what x is. This is the derivative function. This gives you the derivative at any x you choose. So if I say, what's the slope of this function at 19, you know, just plug 19 into that. It's a massive number, but it's not hard to calculate. So that's what I meant by most calculus students, they can calculate these no problem, but then if you had to prove a particular one, so prove, if I had to prove something like x cubed, the derivative of x cubed is equal to 3x squared, that would be a whole other problem for that. But now you know how to do it, you just follow this exact process where you use 3 for n.
You just plug it in.
Yeah, it's going to give you the exact same thing. The whole trick is factoring it out, so you're going to get x minus x naught, and your remaining terms over here are just going to be x squared plus x times x naught plus x naught squared all over x minus x naught. This is going to cancel out with this, so you're going to be left with these terms. When you take the limit as x approaches x naught, you're going to have 3 x naught squareds. 3 x squared. So this is the generic way you do it for any function that looks like this. So you should have no trouble no matter what number I give you. If I do x to any positive number there, you should have no trouble. You should be able to go through this whole process again, that particular number. Right? Makes no difference. All it changes is how this expansion looks.
If we have other numbers thrown in, like 5x cubed minus 3, you just follow the same process. How great.
Yeah, so we'll prove it's a limit. So yeah, so let's think about for a second. Okay, let's give this thing a coefficient. Let's just reason about that. Glad you brought this up because I wouldn't have thought about it. So let's say we were trying to find the derivative of a function like 5x cubed, right? That's what you're saying?
Minus 3.
Minus 3. Okay, remember, we're just talking about a limit, right? So we're going to be able to pull this one out, the 5 out. Let's start with just this. Let's do a very specific case
That
for
makes sense now.
that.
Yeah.
Yeah, but I think seeing this might be worth it. So let's just do it real quick since we got such an easy class today. So we'll find it for f of x is equal to 5x, and we'll just stick with 5x cubed. Well, it doesn't matter if you plus something on, you'll see how it goes out. So we'll put the minus in there, let you see how it cancels. So let's find that thing's derivative by hand. So then, and let x naught be any point in R. So we're just picking some random point in R. We're going to find the derivative of x naught. So then f prime at x naught is going to equal the limit, I won't bother as x approaches x naught, you know that's what's happening, of, and maybe we'll do some parentheses. So in the numerator we're going to have 5x naught cubed minus 3 minus 5x cubed plus 3 now, and you'll see why that 3 doesn't matter now, all over x naught minus x. F of x f of x naught minus f of x all over x naught minus x. With me? So now here's where it becomes the same thing. So the 3's cancel out just in the numerator, and then I can factor the 5 out of the whole thing. So it's equal to 5 times the limit of x naught cubed minus x cubed all over x naught minus x.
Wait.
And then from there on out it's the same thing.
But that doesn't match your signs, does it? 5x cubed, 5x naught cubed minus 5. Oh no, that's, sorry, never mind.
Good?
Yeah.
Because this is still just a limit. And remember that you can factor a constant outside of a limit. It's still, everything we can do with limits, clear back in chapter 2, we can still do with these limits. So we know that we can pull constants out of limits. We can do that with these as well. So this constant being in front doesn't really change anything. It just means you're going to multiply your ultimate answer by 5. So we just barely figured out how to calculate the derivative of this thing, or calculated what this thing was. This was 3x naught squared. Right? This is now just the derivative of x cubed,
Because of that formula.
which is 3x squared.
Right.
That's the one we just did right before this. So this is going to be 5 times 3x cubed squared. Sorry. So just 15x squared. So we can say in general, if you want the derivative of ax to the m, where a is just some constant and n's a natural, so you want the derivative of that, it's going to be a times n times x to the n minus 1. Make sense? All right, let's do some more. Where were we? This one. Prove, okay, so now we're proving that if a function is differentiable at a point, then it's continuous at the point. Now how do I show that a function is continuous? Do you remember how we do that?
You show that if the sequence converges to x, then f of the sequence converges to f of x.
Right, if the sequence converges to x naught, then the image of the sequence converges to f of x naught, was the way we did with the sequence. Or in other words, is if the limit as x approaches x naught of f of x is equal to f of x naught. This is the way we do it with these types of limits. Same exact thing though, right? As the sequence approaches x naught, the image of the sequence approaches f of x naught.
So this is with functions, right?
It's always with functions. We're saying showing that a function is continuous. This is in the domain. As my domain gets closer and closer to x naught, whereas the sequence in my domain gets closer and closer to x naught, the image of my sequence gets closer and closer to the image of x naught. Same thing. So this is ultimately what you're trying to show when you're trying to show a function's continuous. You can do it the way that we've been doing it before, but you can also just do it this way. You can use the limit this way instead of explicitly finding a sequence in the domain and taking the limit of the sequence. Because the exact same thing. So that's what we're going to try to show. So using the fact that function is differentiable. So try out what we're doing exactly. If f is a function from some interval, some neighborhood containing x naught to r, if f by oh, we don't have a particular function. If f from I to r is differentiable, at some point x naught in I, then f is continuous at x naught. Right? That's what we're trying to show. Ultimately, I'm trying to show that the limit as x approaches x naught of f of x is equal to f of x naught. That's ultimately what I'm trying to show. So 1, let f from I to r such that f is differentiable, and let x naught be some point in I. Oh, it's differentiable at x naught. F is differentiable at x naught in I. Okay. So if it's differentiable at x naught in I, what that means is the derivative exists. Whatever that limit is, exists. So then, the limit as x approaches x naught of f of x naught minus f of x over x minus x naught, we know that this is a number. This exists. We don't know what it is, but this is well defined, right? So what is this equal to? Well, this exists. This is equal to some number. We'll call it L for the limit.
So you wrote f of x naught minus f of x, and then on the bottom.
Oh, thank you.
Yeah.
I don't know why I erased all of them. Could just erase the things. Yes. Okay. So I know that this limit, whatever it is, exists. It equals some number L for some L in R. Okay. For some number, right? So then, the limit as x approaches x naught of f of x naught minus f of x, going to move this limit to the other side, is equal to L times the limit of the limit as x approaches x naught of x naught minus x. Right? Just moving this limit to the other side of the equation. Multiply both sides by that limit. It's going to cancel out on this side and move it to the other side. Anything weird there? You just need to look at it for a second?
Oh, okay.
Okay. So now, easy peasy. Over here, what is this limit?
It's just x naught.
It's 0.
Oh,
It's x naught minus x naught.
Right.
So we got 0 over here. So now I've got the limit, and maybe I'll break this one up into 2. As x approaches x naught of f of x naught minus the limit as x approaches x naught of f of x is equal to 0, right? This limit is the limit of a constant, right?
Yeah.
So this is just f of x naught, and I'm going to move this limit to the other side. So the limit of a constant is just f of x naught is equal to, move this limit to the other side, the limit, I should have done the other way, but I think you get it. The limit of this is equal to f of x naught. We're done. It's continuous. Let me rewrite it one more way. So now the limit as x approaches x naught of f of x is equal to f of x naught. Okay, that's rewriting that in a way that we're just seeing it. As x approaches x naught, the image of x approaches the image of x naught. It's continuous.
Just to clarify, if you have a function and you have just a hole in that function, just like 1 point, then you can't take the derivative at that point.
Correct. The function has to be defined there for you to take a derivative there. And I don't know when we're going to do it. We're going to find out if, we just did it. If it's differentiable there, it's continuous there. So it has to be continuous if it's going to have a derivative. It having a derivative implies it's continuous. It being continuous implies it's defined. Right? Because this...
Not always. Right? Because with the
How can it be
right
continuous where that isn't defined?
What is right? What about the absolute value function? Is that continuous, but it's not defined at one point for the derivative?
You're saying the derivative function isn't continuous. The absolute value function is. Just because a function is continuous doesn't mean it's differentiable. But if it's differentiable, it's for sure continuous.
Right.
So the absolute value function isn't differentiable, but it is continuous. That's fine.
Right.
We're saying the other way has to always be the case. If it's differentiable, then it's continuous. But just because it's continuous doesn't mean it's differentiable. In fact, there's a function that's continuous everywhere and is nowhere differentiable. I think the author is going to introduce it at some point, because I think that this was a class where I came across that one too. Anyways, so if a function is differentiable, then it is continuous. Good? Yeah? Okay. So now some basic derivative rules, similar to our limit rules, but a little bit more surprising. So we're going to prove that the derivative, I'm going to use this for taking the derivative of a sum of two functions is equal to the sum of their derivatives. Nice and intuitive, right? And here's where it gets crazy. The derivative of a product of two functions is nothing even close to the product of their two derivatives. Instead, it's the derivative of the first function multiplied by the second plus the derivative of the second function multiplied by the first. Very unintuitive result. Why exactly? In fact, Leibniz, when he was first deriving calculus, he had a note in one of his journals, and I guess it was in there for like a 3-day span or something, where he says, and obviously the derivative of a product of two functions is equal to the product of their derivatives. Nope. That is not the case. And so if someone is genius as Leibniz, intuition can mislead him. Shows us how much we should rely on our own intuition when coming to results. So yeah, we'll prove that. But first we'll do the easy case. Proof. If f, I don't know if we need to know anything about these functions. I didn't write very specifically there. They need to have the same domain. So if f from D to R and G from D to R. So if f and g are two functions that have the same domain, and x naught, if f and g are functions from D to R such that they're differentiable at x naught, such that, not that they're differentiable at x naught in D, then f plus g prime at x naught is equal to f prime of x naught plus g prime of x naught. So if f and g are two functions defined on the same domain such that they're both differentiable at x naught in that domain, then the derivative of the sum is equal to the sum of the derivatives. I don't know if they need to have the same domain or if x naught just needs to be a point in both their domains. One of you guys have your book available?
Yeah.
You want to look at that real quick?
Wouldn't it
See how
have to
it's-
have the same domains?
They could. Their domain just might need to overlap at some point. Because I don't know why they would have to have the same domain. Of course, you could restrict the domains on both of them to where it's the same. So it comes out to the same thing. Never mind, doesn't matter. So this works good enough for all the purposes we're talking about. Because if you have two functions and their domains just overlap, you can redefine the functions in terms of where they overlap, and then this becomes true. Which all we care about is where they overlap anyways. Anyways. 1. So let f and g such that blah blah blah, everything we have there, and let x naught be some point in D. 2. Then f plus g prime at x naught is equal to what we get when we plug x naught into this function. What do we get when we plug x naught into this function? We get f of x naught plus g of x naught minus what we get when we plug x into this function, f of x minus g of x all over x naught minus x. Limit. Sorry. Right? Nothing weird so far? And then that is going to be equal to, obviously you can split derivatives. Well, I'll rewrite the term first and I think it'll be obvious what I'm trying to say. So we can rewrite this as f of x naught minus f of x plus g of x naught minus g of x all over x naught minus x. And then if I have terms over the same denominator, I can separate those terms. So this is equal to the limit of, maybe I'll write it like this one more time to help really stress it. F of x naught minus f of x over x naught minus x plus g of x naught minus g of x all over x naught minus x. Okay. You good with that separation there?
And is that as simplified as it can get?
Well, the point is, now I can split this into two limits, and I know how to calculate each of these limits. Let me do one more step, and then I think it'll be obvious what we've got now. So this is equal to the limit, because the limit of a sum is equal to the sum of the limits. So this is the limit of f of x naught minus f of x over x naught minus x plus g of x naught minus g of x over x naught minus x. Limit, sorry. Plus the limit. But what is the limit of x naught minus x? Oh, of x naught minus...
I don't know, what is it?
Let me put this in here as well. As x approaches x naught.
Is it f?
It's
What is this limit? It's what?
That right there. F with the little squiggly line on it.
Oh, we call that f prime.
Yeah.
So yeah, f prime of x naught. That's exactly what f prime of x naught is defined to be. That limit. So that is f prime of x naught plus, and this limit is exactly what g prime of x naught is. Right? That's the exact definition we gave a derivative. F prime of x naught is this limit. F prime of x naught is this limit. And we're done.
Easy peasy.
Easy peasy. You know, look out for a sec.
I think I got it.
Okay. So now let's do the same thing, except for now we're doing the product. So then f times g prime is equal to f prime of x naught times g of x naught plus g prime of x naught times f of x naught. And you'll memorize this formula. And so the way that we say it is the derivative of a product is equal to the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. Let's say it's an action real quick. Where might you use this? Let's do it with one that we know how to calculate the derivative of so that we can quickly see it comes out the same. So let's say we're looking at 3x squared times 2x cubed. Now we know we could just combine this real quick, so let's do it with what we already know. I know that I can rewrite this. This is the same thing as 6x to the 5, right? And we know how to take the derivative of this. Just pull that down to minus 1. So that's equal to 30x to the 4. Now I'm going to do this again using this formula and see that I get exactly the same thing, 30x to the 4, just to help you see a demonstration of the formula. Obviously, we wouldn't actually use a formula in this case. So this is equal to, so we're saying the derivative of the first multiplied by the second. So what's the derivative of this?
6x.
6x. So the derivative of the first multiplied by the second plus the derivative of the second. What's the derivative of this?
6x squared.
6x squared multiplied by the first. So now simplify. 6 times 2 is 12x to the 4 plus 6 times 3 is 18x to the 4 is equal to 12 plus 18 is 30x to the 4. Crazy, it worked. So the formula appears to work. There's an example of using the formula in a case where we never actually use it, but there it is. And now we'll prove the formula. So we're looking for the derivative of f times g prime at x naught. That is going to equal the limit as x approaches x naught of, plug in x naught to that, we're going to get f of x naught times g of x naught minus f of x times g of x all over x naught minus x. Any questions on just plugging in? Okay. So then that is equal to, how can I motivate what I'm about to do? I am trying to get an f of x naught minus f of x over this, and a g of x naught minus g of x over this. Because then those are just derivatives, I know how to take those limits. So I need to get an extra term in there so I can factor out, maybe I'll just do it and then try and help you see it. I don't know if it's helping to try and motivate it. I think I'm reading it. So that's equal to the limit. Basically, I'm going to add and subtract the same thing from the numerator. And you're going to see how it lets me factor.
Right.
So I'm going to do minus, here's where I'm adding the term, I'm going to minus f of x naught g of x. And then I'm going to plus f of x naught g of x. And then I have minus f of x times g of x all over x naught minus x. So I added and subtracted this term from the numerator, thereby not changing anything. And why did I do that? I did that so now I can factor an f of x naught out of these two terms, leaving a g x naught minus g of x. And I can factor a g of x out of these two terms, leaving an f of x naught minus f of x. And then those are going to be derivatives I know how to calculate. So this is equal to, I'm going to maybe start by splitting this into two limits. That will probably be more useful. Limit as x approaches x naught of f of x naught times g of x naught minus f of x naught times g of x all over x naught minus x plus the limit as x approaches x naught of, and I still need these two terms, f of x naught g of x minus f of x g of x. Fair warning, I'm 90% sure I have you prove some of these on your tests, and I'm almost 99% sure I have you prove this exact one on your test. So, be ready to prove this. Anyways,
You just use the sum of limits there?
yeah, the limit of a sum of two terms is the same thing as the sum of their
So
limits.
You haven't factored that out yet.
So I didn't do any factoring yet. Yeah, I thought, because I'm going to be factoring out two different things from different terms. So now, on the right-hand side, notice f of x naught is just a constant. So I'm going to factor that outside the limit. So this is equal to the limit as x approaches x naught. Oops. Said I was going to factor it out, decided not to. This is equal to f of x naught times the limit as x approaches x naught of, now we just have g of x naught minus g of x over x naught minus x. Yay, that looks familiar. And then over here, I'm going to factor out the g of x, but the g of x isn't a constant. So I still need to take the limit of it. So I'm using the fact that the limit of a product is a product of the limit. So see if this needs more clarification. If it does, I'll explain more. The limit as x approaches x naught of g of x times the limit as x approaches x naught of f of x naught minus f of x all over x naught minus x. I have it backwards here. The first term should be x naught, the second one's x.
Why is g of x not a constant?
G of x, because our x is what's changing. We have a sequence that is being represented by this x that gets closer and closer to x naught. X naught's a number. Like when we were doing it before, we started with like proving that, no, we did that, it wasn't at a particular number. But yeah, x naught's some number in the real numbers. We pick some x naught in our domain, it's just some number.
Okay.
Now we're doing it as x gets closer and closer. So x is what's varying, x is what we need to take the limit of. X naught, that's just a number.
Right, okay.
So yeah, we pulled the gx out of both these terms and then pulled it outside the limit, but it still needs its own limit. So we did the fact that the product, the limit of a product is a product of the limits. But now we know how to calculate all these limits, right?
Yeah.
So f of x naught is still just f of x naught. That doesn't change. So it's equal to f of x naught, that doesn't change, times, what's this limit?
G prime of x naught.
G prime of x naught, perfect. What's this limit?
G of x naught.
Just g of x naught. And what's this limit? F prime of x naught. Which is equal to, if we change the order, use the fact that multiplication and addition are associative and commutative, f prime of x naught, this is the way we typically remember it. But it's the exact same thing. F of x naught. Same thing. And we're done. Good? Think you'd be able to reproduce that on test?
Not right now.
Well, better go back and watch the lecture a lot, or read the book. The author has proofs of all of these, I think. Okay, next one. So, next one's kind of like a little lemma for the one that follows it, but I guess it's useful in its own right, so we'll have to kind of erase from scratch. So, let g be some function from d to r such that g of x is never equal to 0. Because we're proving this one. So g is going to be in the denominator. We need to restrict it so that's never 0, so that we're never dividing by 0. You with me? Then, if g is differentiable at some point x naught in its domain, then the derivative at that point the derivative of 1 over g prime at that point is equal to negative g of x naught over g of x naught squared. No, prime in the numerator, right? Prime, yeah. So if g is some function that isn't 0 and it's differentiable at x naught, then the derivative of 1 over g, its inverse, well, no, not inverse, because we have inverse mean something different with functions. It's reciprocal function, maybe I could say call that. The derivative of its reciprocal function is just this. So let's do a concrete example. Let's say I'm looking for the derivative of 1 over 3x cubed. So I'm looking for the derivative of this. Here's my g of x. And we'll do it at a point. We just can't pick the point where x is actually equal to 0 here, right? So we're saying that this then, that its derivative, it turns out, is going to be negative, what's g prime? G prime is 9x squared all over g at x naught squared. So that's going to be this function squared, which is going to be 9 times x to the 6. That's using the formula. So we're going to prove the formula. With me? And obviously that formula only works where x isn't 0. Because then g of x is 0. Okay, so let's prove it. Let g from d to r such that g is differentiable at x naught in d and g of x naught is not equal to 0. So then 1 over g prime at x naught is equal to, what's this equal to? Let's get you guys plugging in actual formulas. This is equal to the limit as x approaches x naught of,
is it 1 over g of x naught minus 1 over g of x?
perfect, minus 1 over g of x all over x naught minus x. Just plugging in so far, right? Just plugging into this function. You good?
Oh, okay.
So now, yeah, remember that g of x is just in the denominator. That's how we define it. It's not the whole function, it's just what's down here. Anyways, so now what's this equal to? Well, obviously first thing we want to do is get a common denominator in the numerator. That sounded weird, but that's what we want to do. So that's equal to, get a common denominator up here, and we're going to get g of x minus g of x naught all over g of x naught times g of x all over x naught minus x. Okay, bit of fraction stacking there, but you follow the thinking? Nothing weird? Okay. Now, back to what you know about fractions. If I have this divided by this, that's the same thing as this times the reciprocal of this. So make sure you understand the algebra here. That's equal to the limit as x approaches x naught of g of x minus g of x naught all over g of x naught times g of x times x naught minus x. You follow that? Because we multiplied this by 1 over x naught minus x, which gives us this.
No.
No, it needs to use the
Reciprocal.
reciprocal.
Okay, so if I have a over b all over c, right? Then that's the same thing as a over b times 1 over c, which is a over b times c.
Well, that's not the reciprocal though, but yeah, that makes sense.
Well, I meant the reciprocal of the denominator, which is this, is what we multiply the numerator by. Multiply the numerator by the reciprocal of the denominator.
Okay.
Multiply the numerator by the reciprocal of the denominator.
That makes sense.
Anyways,
That was confusing, but that makes sense.
yeah, that's the algebra. Okay, now, let's see. I'm going to split this down to two limits, to two products. I'm going to do 1 over this term times this term over this term. So instead of having it as a over b times c, I'm going to rewrite it as 1 over b times a over c, except for as limits now. Follow me? So this is equal to the limit as x approaches x naught of 1 over, pulling this out, maybe we'll do brackets still, 1 over g of x naught times g of x, all times the limit as x approaches x naught of
G of x
g of x minus g of x naught over x naught minus x. Right? And that's equal to, okay, the first term, remember, g is a function such that it's not 0 at x naught. So I know how to take this limit now. Right? So what's this limit?
1 over 2.
G of x naught squared.
Oh, yeah.
Right? G of x naught times g of x naught.
Right.
1 over g of x naught squared is this limit. Times now, notice that the second limit, we can almost do it. We have g of x minus g of x naught. We want the numerator to have a g of x naught minus g of x.
So you multiply by -1.
So multiply by -1. So I'm going to multiply how would be the easiest way to say this? I'm going to factor a -1 out of this. Maybe that's the easiest way to say it. I'm going to factor a -1 out of this, so that's going to make this one negative and this one positive. Does that make sense?
Yeah.
Okay. So then this is this times, I'm factoring out the -1. So times, remember, if you factor out a constant, you can pull it all the way out of the limit. So -1 times, now we have the limit as x approaches x naught of g of x naught minus g of x all over x naught minus x. And obviously we know what this limit is. G prime of x naught, right? So So now we have negative g prime of x naught, so this whole thing is equal to negative g prime of x naught all over g of x naught squared, which is what we're trying to prove. You good?
I think you lost me in the algebra philosopher.
So going from here to here, so you're good with just evaluating this limit. Okay, so it's pulling out the negative 1 that's throwing you off. The easiest way to see it is plug the negative 1 back in. If I plug the negative 1 back in, that makes this negative and this positive, and then switch their locations.
Why did we have to do that in the first place?
Because we know what this limit is. We don't know this limit. Notice where the x naught is. This is g of x minus g of x naught. Another way that we could have done it, it's the exact same thing, was pull the negative out of the denominator and flip those around, and then taking the limit, but I thought that might be more confusing. Good?
Yeah.
Okay. So, now let's do it generically when we're talking about a quotient. Alright, so now let's prove where f and g are functions that are continuous at x naught such that g of x naught is not equal to 0. Then we're proving that f over g prime at x naught is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared.
So this one's not on the test, right?
It could be. The product one was for sure. This one could be. But this one's just using this one and the product one, this one and the product one together. So this one's actually really easy once you have the other two. But this is one that, this is the second one that every calculus student, third one I guess. Every calculus student memorizes this. Every calculus student memorizes this, and every calculus student memorizes this. One of the, what are they called? Helpful things that you memorize to help you remember the actual formula. I can't remember what they're called. They remember low d high, high d low. Square the bottom, away we go. Low d high, high d low, square the bottom, away we go. Low d high minus high d low, square the bottom, away we go. Something like that. There's supposed to be a tune to the song, but I can't remember. But those are the words. Low d high minus high d low, square the bottom, away we go. Okay, but, so this formula. See this formula in action real quick, I guess, with one that we can already just do in our brains to make sure that's working. I'll do something like, we'll look at 6x cubed over 2x, and we already know, okay, you can cancel that out. That's the same thing as just 3x squared, right? And so the derivative, when we're all said and done, should just be 6x. The derivative of this is just 6x. Just doing it the way that we already know. I haven't used the formula yet, so don't see how I'm trying to plug into the formula. I just reduce that. That's really the same thing as that. Then bring the 2 down and minus 1. There's just a 1. Good? So now let's do this with the formula up there, making a mess of everything, but see it comes out the same. So we have the bottom times the derivative of the top. What's the derivative of the top?
8x squared.
Times 18x squared. So the bottom times the derivative of the top minus the top times, what's the derivative of the bottom?
2.
2, right? So we're trying to find the derivative of 2x to the 1, bring the 1 down, and then, so the derivative of this prime is equal to 2 times, bring the n down, 1 times x to the 0. X to the 0 is 1. When we're all said and done, it's just 2. So yeah, you're right. Times 2. One thing I don't think we talked about, what's the derivative of a constant? What's the derivative of 2?
2.
It's 0. 2 can be thought of as 2 times x to the 0, right? That's still just 2. Okay. And now, use the rule that we know. The derivative of that is 2 times 0 times x to the minus 1, which is 0. Right? Looking at it graphically, look at the equation f of x is equal to 2. What does that look like? That's just a horizontal line. Any constant, its graph is just a horizontal line. What's the slope of a horizontal line? 0. It doesn't have a slope. That's what we mean by horizontal.
So if you were, this is kind of, might be a weird question. If you were to like take a sequence that was just the derivative of a derivative of a derivative of a derivative, you'd be approaching 0.
You could be. If it was a polynomial, then yes. If you have an nth degree polynomial, then its nth derivative is 0. Or is that a constant? And its nth plus 1 derivative is 0. You eventually get to 0.
You eventually actually reach 0, right?
Yeah.
Okay.
The nth plus 1, the n plus 1th derivative, I don't know how to say that, would be 0. Yes. Okay, we're finishing this. So, bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, right? And what's that equal to? 2 times 18 is
36.
and x cubed minus 12x cubed all over 4x squared, which is equal to 36 minus 12 is 24. 24 divided by 4 is 6. So when we cancel it all out, we're going to have 6. And instead of x cubed, we get rid of 2 x's. So it's just 1x left over, which is what you could have guessed, because you can do the math in your head so fast. Okay, so let's actually prove this thing. Okay, so when we're looking at f over g prime at x naught, we can rethink about that as 1 over g times f prime at x naught, right? And now we use the product rule. We know how to find the derivative of a product, and we know the derivative of 1 over g. So let me just write it using the product rule real quick. The product rule is the derivative of the first prime, the derivative of the first multiplied by the second, plus the derivative of the second multiplied by the first. You with me? Now we know what this thing is. So this is equal to, substituting in for 1 over g prime at x naught. 1 over g prime at x naught is negative g prime at x naught all over g of x naught squared. And this is times f of x naught plus f prime of x naught over g of x naught, yes? It's an easy way to write it. Right? Just plugging in. And so from here on out, it's just algebra. Get a common denominator, and then we'll write this term first. One step at a time. I'm going to multiply this one top and bottom by g of x naught. Just g of x naught. So this is equal to, we'll keep the first term, but now I'm going to write that in the numerator. So I have negative g prime of x naught times f of x naught all over g of x naught squared plus, and I'm multiplying this one top and bottom by g of x naught, so f prime of x naught times g of x naught all over g of x naught squared. So now I have a common denominator. I can write them both over the same denominator. And I'm going to write this term first and then this term. So I'm writing this term first, so I'm going to write the g before the f. So g of x naught, then I'm going to write my f prime times f prime of x naught minus now this term. And I guess I'm going to swap the order on these two. I'm going to write that as f of x naught times g prime of x naught. And then they're all over g of x naught squared. And we're done. That's what we're trying to show. So this one actually wasn't that bad. Right? Questions?
Can we just do our proofs like that and not have to like say?
No, you need to say. I want to make sure you understand the conditions under which it's true. I just don't want to write it all out, the same conditions every time. But no, I want you to understand the conditions under which the proof is valid. But most of the times, it's exactly what you would expect for the proof to be valid. Okay. Our last proof is now proving that the derivative of x to any integer now, say negative 19, what's the derivative of that? We're going to prove that the derivative of that is negative 19 times x, and subtract 1 from that, negative 20. So we know that this worked for natural numbers, now we're going to prove it works for integers in general.
Are we gonna prove it for, not just integers, like for 1/2, for example?
For rationals, let's think. I don't know. We will get to rationals because we haven't talked about inverse functions yet. And so if I want to think about 5/2, the half is really the inverse of squared. The next section is going to be talking about inverse functions. So I think we'll be proving this for rational functions next week.
I see.
But let's prove it for any integer. Let a in z, comma, and let f be a function from R to R. I think we're fine doing it that way. Yeah, because we don't have to worry about inverse functions yet. Let f be a function from R to R by f of x is equal to x to the a. Then f prime of x is equal to a times x to the a minus 1. Okay, so let's prove it. Let a in z, comma, and let f be a function from the real numbers to the real numbers by f of x is equal to x to the a. 2. Okay, we've got two cases. Either a is greater than or equal to 0, or it's less than 0. If a is greater than or equal to 0,
Wouldn't it be,
then we're done.
wouldn't you want to split it up by a is greater than 0 and then a is less than or equal to 0?
No, we did it for the case. This case works for n greater than or equal to 0. So it also works for the case for n is 0, because that's the derivative of a constant. Right? So we already know for a greater than or equal to 0, we already have handled those cases, we're done. So all we really care about is what do we do with negative exponents, right? Assume a is less than 0. So if a is an integer less than 0, by definition, then there exists n in the naturals such that negative n is equal to a. Right? It's what it meant to be a negative integer. You're equal to the negative, the additive reciprocal of a natural number. Then f of x equal to x to the a is equal to x to the negative n is equal to, using what we did, I don't know if it was last week or the week before, 1 over x to the n. Right? So f of x is equal to that. Let x naught, well, maybe we can just take its derivative directly. We don't need to do the x naught because we know how to take the derivative now. So then 1 over xn prime is equal to, the derivative of that is what?
The theorem right there.
Yeah, it's the thing sitting right here. It's equal to negative, the derivative of this. What's the derivative of the denominator?
N times x to the n minus 1.
N times x to the n minus 1, all over this thing squared, or x to the 2n. You follow that? We're just using this formula right here. The derivative of this, negative the derivative of this, over this squared. Anything weird? Okay? So then this is equal to, if I move this back up to the numerator, it makes the exponent negative, right? So this is equal to negative n times x to the n minus 1 times x to the negative 2n. When you multiply terms together, you add their exponents. So I'm doing n minus 1 minus 2n. Let's first do n minus 2n is negative n minus 1. So it's equal to negative n times x to the negative n minus 1, right? Which is equal to, substitute back in for a times x to the a minus 1. Remember, a is negative n. And we're done.
Nice.
Okay, and then the last corollary that he puts in there is just that all rational functions are differentiable, where the denominator isn't 0. So if the rational function is defined, then it's differentiable. Let's make sense of that real quick. Do you remember what a polynomial is? A polynomial, f of x, it's a function that can be expressed as the sum from n equals 0 to n, I equals 0 to n, of a sub I times x to the I. Example, let's write a concrete one. Here's an abstract way of writing a second degree polynomial. This is an nth degree polynomial. Let's explicitly write out a second degree polynomial. It's a sub 0 times x to 0 plus a sub 1 times x to the 1 plus a sub 2 times x to 2. There's a second degree polynomial. A0, A1, and A2 could be any real numbers you want, and then x's are operating as functions. Obviously, x to 0 is always 1, so this is a to the 0 plus a to the 1, x1 plus a to the 2, x2. Any function you write that has this form is a polynomial. Here's a concrete example, 5 plus 13x squared. There's a second degree polynomial. Notice that a1 in this case was 0. So we had a0 was 5, a1 was 0, a2 was 13. So pick any real numbers you want for these three numbers, you have a polynomial. Let's try another polynomial, in case you're confused by what the numbers can be. Pi plus e times x plus the square root of 19x squared. Still a polynomial. Some number plus some number times x plus some number times x squared. Still a second degree polynomial. This is how we generically write out an nth degree polynomial. So, what we're saying, the corollary is that, well, first off, let's just look at a polynomial and see why it's always differentiable. We already proved it's always continuous, but it's also always differentiable. Its individual terms are all differentiable, right? Each one of its terms, anytime you have a term, a x to the n, that's differentiable. We know how to find it. And this is just a sum of a bunch of those. So that sum is differentiable. And then same thing with the denominator. Well, now let's write it out. What would it be? So if I'm looking for the derivative of f of g, and I know now that those are polynomials, this is equal to, we have the formula for this, g of x naught times g prime of x, times f prime of x naught, minus f of x naught times g prime of x naught, all over g of x naught squared. Now, all the corollary is saying is that all rational functions are differentiable, or that you're guaranteed that this is always defined as long as the point you're doing it at, g of x isn't 0. So in our case, if g of x naught isn't 0, then we're good. How do we know? This is a function, so g of x naught, that's always giving us a number, so we're good here. F prime of x naught, that's the derivative of a polynomial. We know that the derivative of a polynomial always exists, so that's fine. This term's fine, this term's fine, and this term's fine as long as we're not 0. So the whole thing's fine as long as the denominator is not 0. Make sense? So polynomial functions are really nice. Rational functions, which are just ratios of polynomial functions, are really nice. We know they're everywhere continuous as long as the denominator is not 0. Now we know they're everywhere differentiable as long as the denominator is not 0. So polynomial functions we really like. Good? So that's the end of the section. You can get started on the homework. Unless you had any questions that you want recorded first. Okay. Turn in all your stuff from your never-ending